Welcome students of Sanmati Engineering College. Imagine the universe as a giant Lego set. Just like Legos connect to build amazing structures, atoms join together to form everything we see and touch. But how do these tiny building blocks create such diverse materials? The answer lies in the fascinating world of energy bands. Inside each atom, electrons orbit the nucleus at specific energy levels, like planets around a star. When atoms come close together in a solid, their individual energy levels interact. This interaction creates a continuous range of energy levels called energy bands. Think of these bands as highways for electrons. Some highways are crowded with electrons while others are nearly empty. The way these highways are filled and connected determines whether a material conducts electricity, insulates against it, or falls somewhere in between.
In the bustling city of an atom, the valence band is like the crowded downtown area. This band represents the highest energy levels occupied by electrons at absolute zero temperature. These electrons are responsible for the chemical bonding that holds atoms together. Imagine these electrons as tiny links, connecting atoms together in a vast network. The strength and arrangement of these links determine the material's properties, like its melting point, hardness, and even how well it conducts electricity. The valence band is crucial for understanding how materials behave. It's the starting point for electrons to gain enough energy to move freely and conduct electricity. Without the valence band, our electronic devices wouldn't exist. Above the crowded valence band lies the conduction band, a wide open highway with plenty of room for electrons to move freely. Think of it as the expressway outside the city, where cars can zip along without traffic jams. At absolute zero temperature, the conduction band is usually empty. However, when we apply energy to a material, like heat or light, electrons in the valence band can absorb this energy and jump to the conduction band. Once in the conduction band, electrons are no longer bound to individual atoms. They can move freely throughout the material, carrying electrical current with them. This is what allows metals to conduct electricity so effectively.
Between the bustling valence band and the open expanse of the conduction band lies a crucial region called the forbidden gap. This gap, also known as the band gap, represents a range of energy levels that electrons are forbidden from occupying. Think of it as a tall fence separating the crowded city from the open highway. Electrons need enough energy to jump over this fence to move freely in the conduction band. The size of this forbidden gap determines a material's electrical conductivity. In insulators, the forbidden gap is large, like a towering wall. Electrons need a significant amount of energy to overcome it, making it difficult for them to conduct electricity. In conductors, the gap is very small or even non-existent, allowing electrons to flow easily.
Section 5. Covalent bonds. Sharing is caring for electrons. In the world of atoms, sharing is caring, especially when it comes to electrons. Covalent bonds, the glue that holds many materials together, are formed when atoms share electrons in their outermost energy levels. Imagine two atoms holding hands with their shared electrons forming the bond between them. This sharing creates a stable configuration where both atoms have a filled outer shell of electrons. These shared electrons contribute to the formation of energy bands. The strength and directionality of covalent bonds influence the shape and properties of materials. For example, the strong covalent bonds in diamond give it its exceptional hardness, while the weaker bonds in graphite allow its layers to slide past each other, making it an excellent lubricant.
Section 6. Semiconductor vacancies, holes in the crowd. Imagine a crowded concert hall where everyone is seated except for one empty chair. This empty space, or hole, allows people to move around more easily by shifting from one seat to the next. Similarly, in semiconductors, electron vacancies create holes that act as positive charge carriers. When an electron in the valence band gains enough energy to jump to the conduction band, it leaves behind a hole. This hole behaves like a positively charged particle, attracting nearby electrons. As electrons move to fill the hole, they create new holes, allowing a flow of positive charge. This unique property of semiconductors, where both electrons and holes contribute to electrical conductivity, forms the basis for transistors, diodes, and other electronic devices that power our modern world.
Section 7. bound versus free electrons, stuck or mobile. In the realm of materials, electrons are like tiny particles with different levels of freedom. Some electrons are bound to their atoms, like prisoners confined to their cells. Others are free to roam throughout the material, like travelers exploring a new city. Bound electrons occupy energy levels in the valence band and are responsible for holding atoms together. They cannot contribute to electrical conductivity because they are not free to move long distances. Free electrons, on the other hand, reside in the conduction band and are not tied to any particular atom. They can move easily through the material, carrying electrical current with them. The number of free electrons in a material determines its conductivity. More free electrons mean higher conductivity.
Section 8. Material classification, a spectrum of conductivity. Not all materials are created equal when it comes to conducting electricity. Some, like copper, are excellent conductors, while others, like rubber, are insulators. Energy band theory provides a powerful framework for classifying materials based on their conductivity. Conductors have overlapping valence and conduction bands, or a very small forbidden gap. This allows electrons to flow freely, making them excellent conductors of electricity. Metals, with their sea of free electrons, are prime examples of conductors. Insulators, on the other hand, have a large forbidden gap between the valence and conduction bands. This gap acts as a barrier to electron movement, making it difficult for them to conduct electricity. Materials like glass and rubber are good insulators. Semiconductors fall between conductors and insulators with a moderate forbidden gap. This gap can be overcome by providing external energy, such as heat or light, allowing them to conduct electricity under specific conditions. This unique property makes semiconductors essential for electronic devices.
Section 9. Energy band diagrams, a visual guide. Imagine trying to navigate a complex city without a map. Energy band diagrams serve as visual maps for understanding the electronic properties of materials. They graphically represent the energy levels available to electrons in a solid. These diagrams show the valence band, conduction band, and forbidden gap, providing insights into a material's conductivity. The position and width of these bands reveal information about how easily electrons can move and contribute to electrical current. By analyzing energy band diagrams, scientists and engineers can predict how materials will behave under different conditions, leading to the development of new and improved electronic devices.
Section 10, Band Theory in Action, from transistors to solar cells. Energy band theory isn't just an abstract concept confined to textbooks. It plays a vital role in countless technologies that shape our modern world. From the transistors that power our smartphones to the solar cells that harness the sun's energy, band theory is the driving force behind these innovations. In transistors, the controlled flow of electrons between different semiconductor regions, made possible by manipulating energy band gaps, allows for the amplification and switching of electronic signals. This forms the foundation of modern computing and communication technologies. In solar cells, the absorption of light by semiconductor materials excites electrons across the forbidden gap, generating an electric current. By carefully engineering the band gap of materials, scientists can improve the efficiency of solar cells and pave the way for a more sustainable future.
Section 11. Unlocking the secrets of matter, the power of band theory. Understanding energy bands in solids is like unlocking a secret code that reveals the hidden language of matter. It allows us to comprehend the fundamental link between the microscopic world of atoms and the macroscopic properties of materials. By applying the principles of band theory, we can design materials with tailored electronic and optical properties. This ability to manipulate the building blocks of matter at the atomic level has revolutionized electronics, optoelectronics, and countless other fields. As we delve deeper into the mysteries of the quantum world, energy band theory will continue to guide us in our quest to understand and harness the remarkable properties of matter.